So I will talk about stretchable printed circuit boards and wireless medical technology, and especially on the SINTEC module and the Smart Patch PCB technology we have developed in our European project, together with partners like Warren Hub. Like Evalan joining us here. So the technology is taking rigid and flexible printed circuit board technology to soft and stretchable compliant technologies that should be conformable and comfortable on your body. Our objectives is to provide soft stick and stretchable sensor patches where we can use the technology multiple times at longer periods for anyone, anywhere, and any time, and that they should be so robust that they can be dynamically compliant, water repellent, permeable, encapsulated, that it permits an active life. You can have vigorous action, sweating, water activities. And we are also bringing in groundbreaking sensor node technology by the FAT IBC communication, which secure communication and provides large bandwidth at low power. The applications are both in medical and sports performance. So let's go into smart patches. Today it's a booming market. From 2019, when it was $5 billion in size, already last year it had doubled, and then it was estimated to triple again until 2030. But it looks actually it's growing faster than that, at least now. The main markets are in remote patient monitoring for diabetes and heart conditions. And you are combining multi-use modules with disposable patches, where you have flexible wire boards, rigid modules, and compliant patches. Here, if you look to heart monitoring, going from traditional ECGs, you have a plethora of alternatives with implantables, wearables, and portables, and more providing remote patient monitoring. If we look to smart patch hardware technology, it's really not the electronic tattoos that have been presented in research, because there you need to have extremely low power management. You have to use near field communication for bringing enough energy, and extremely small electronic systems for doing anything. No, it's rather rigid flex printed circuit boards that are packaged in elastomers and then flex laminated with compliant fabrics and batch produced printed wire board technology. To the left, you see the backside of MC10's wireless RF sensor, and to the right, a disposable sensor patch produced by Biocore for bioimpedance measurement. And then you put on a rigid electronic platform on top of that can be reused. The SINTEC hardware offering is soft and stretchable sensor patches. We are using thin and soft multi-use modules, and the module is set under the patch for comfort and protection. So on the upper, you see a long flexible cable with a electrode at the end. In the lower left, you see a multi-use sensor module connected with a flex cable to a printed wire board electrophysiological system that is onto a sports tape adhesive. Then you just fold the module into it and it's protected by the adhesive. To the right, you see a module which is just protected by passive sports tape. So the SINTEC technology, we are using solid mount technology, those that are used ordinarily for assembly of printed circuit boards for rigid devices that are used in the subsequent manufacturing of the cardiac monitoring and the module, and below used for additive manufacturing of the stretchable printed wire board for smart patches. Now, for those that are not familiar with it, printed circuit boards are more advanced multi-layered structures where printed wire boards have very few wires and usually just one layer of interconnects. In our manufacturing today, we have established a semi-automatic production for large area rigid stretch printed wire boards using production platforms of Mycronic, one of the partners in the project. We have introduced flexible interface between the rigid and the stretch, and we can do precise patterning of liquid metal alloys for stretchable interconnects with line width below 0.1 millimeter. Yes, the interconnects, and the special thing here is that we're using liquid metals instead of meandering thin film rigid metals. So the liquid metals, just as they are liquid and has a very high flowability, will adjust when you stretch the elastomer and in principle have infinite stretchability. It's the stretchability of the elastomer that decides how long you can stretch it. If you want lower cost and you can allow lower resolution, we have proof of concept also using non-contact deposition with jet dispensing. This decreased the patterning time by a factor of 8. And today it's not material cost that sets the limit of cost today, but rather the capital cost and how much you can produce, the throughput in the machines. Still, we are talking about tens of cents per patch. Our recent improvements are that to allow for vigorous movement and heavy sweating, which had been challenging, especially to improve the capability in sports applications, we had, as I mentioned, start using sport tapes. We're using molded protective encapsulation of the multi-use module. We have a new flat contact to connect to the electrophysiological patch. This is very much also to reduce the total costs. And we have changed from coin battery formats to LiPo batteries used in smartwatches, much improved the robustness of the multi-use modules. For this, we have shown bioimpedance measurements for breath rate monitoring and ECG electrode measurements, also using this long stretchable flat cable to get higher signals, better signals, adopting this soft digital wire board technology for fabricating of long stretchable cables. Although we do not need it for our demonstrators, we had an objective to show multi-layer digital printing of these stretchable systems. And we have shown so with line width below 0.1 millimeter, pitch below 0.5 millimeter, and vias in the sizes just above 0.2 millimeter. My take-home message to you are in hardware, the SINTEC Smart Patches are using multi-use modules with disposable patches. We have STMicroelectronics sensor board platforms, so we can measure motion, pulse, ECG, bioimpedance, and temperature. We have the rigid stretch printed wireboard based sensor patches with wireless electrophysiological readouts printed by Micronics technology. We can apply these to sport tapes, providing a skin adhesive that is smart patch, well suited for active motion. And once again, the large area manufacturing can be used directly from the surface mount technology machines. And something happened here. And with that, I thank you for the attention.
All right. Thank you, Professor Yacht. So there is a question from the audience for you, Professor. So how invasive may be the smart patch?
It has no invasiveness since it is very soft and very compliant. It's a totally stretchable system. Yes, you could say that these modules could have some disturbance, but they can easily set under a tracksuit for sports, and the weight is much lower than, for example, a sport watch. So it has a much less invasiveness than, for example, smart watches.
Thank you very much. So we may proceed if there is probably there is another question from another person from the audience. Is it possible to receive the slides after your speech, Professor? Anyway, we will try to provide them.
There is no problem from me.
We will do our best to share the presentations, so don't worry about this. We will see it later. Thank you, Professor.
Yes, we can put it on the SINTEC homepage later.
Yes, that's for sure. There is another question from Amireza Zayeh. Is this method capable of printing, modifying on the normal fabrics? Can they be waterproof?
The printed wireboard technology is waterproof. The sensor modules are also waterproof. We have used application technology to adhere such systems to fabrics, but we do not have a large experience on this. These are especially made for patch technology.
Okay, thank you very much. So if there is no other question, okay, another question. Can we include any shielding in this technology?
It depends where you would like to have the shielding. It's rather easy to bring in the shielding in the multi-use module. If you want shielding over the whole printed wireboard, it's very much a question about which frequencies. We have difficulties to make a shielding area which is not created by a grid but needs to be totally closed shielding plane. But if you can allow a high density grid plane as a shield, it is possible to do. However, digital printing is a serial printing. So if you need very large areas with high resolution, it will not be very low cost. Then I would recommend other kinds of printing technologies. We are using spray printing through masks for the same kind of qualities, these stretchable systems, but then in batch production. This is an alternative, not well suited for personalized medicine, but if you have very high volumes, it is useful.
Okay, thank you very much. So we will proceed with Alessandro Gumiero. Alessandro currently works in ST Microelectronics, where he developed his skills in electronic design and acquired new expertise in the analysis of biological signals. His research focused on the detection of photoplethysmography, PPG, signal on the wrist in motion condition, both with traditional techniques and recently with more innovative sensors, like single photon avalanche diodes and SPAD cameras. So Alessandro, thank you very much for joining us. You are muted. Okay, now you are unmuted. So the stage is yours. Thank you very much.
Okay, thank you. Can you hear me? I try to share the presentation. Okay. Let me know if you are able to see the presentation or the notes.
Not yet.
Maybe the presentation now. Let me know when you see it. Okay. Can you see me?
Still we cannot see it.
Not. I try to do again. Just a moment.
Okay, now
Okay.
we're seeing something. Go to presentation mode and
Okay. Now you see my slide or the notes?
yes, you may enlarge it to full screen, probably. Yes, thank you very much.
Okay, sorry for the inconvenience. Okay, so as Claudio already said, I'm Alessandro, and now in this presentation, I'm trying to present you the electronical part of the SINTEC project, but just to, I will try to give to you some information about what we developed on the point of view of the boards, the PCB in this project, but also I'm giving to you a little presentation, a little introduction about our group and our company, because it's important to understand why we are studying in this field and why it's important for us to understand this problem about stretchability and wearability of the components of the devices, and what is important to address this kind of thing. Maybe you already know something about ST, obviously, but it's not a common thing because ST is a very large company that work from sand to cloud. It's a very nice, I have to say, slide, but it's quite true. It's a company that work, let me say, from the silicon, from the ingot of silicon, starting from the wafer, arriving to the not to the cloud, obviously, not to the cloud, but work a lot on the embedded firmware and embedded hardware, so on the edge computing. What I want to say is that it's quite strange to find ST in this kind of project, and you can ask why ST is interested to understand on the stretchability on the final device, because ST does not produce final devices and these kind of things, and you cannot find a mobile phone branded as ST, but the integrated circuits coming from ST are inside the mobile phone. So it's important to understand this kind of things. You can again find ST everywhere, but also nowhere, because you can find on the smartwatch, in your house, in the industries, very important field, but you cannot find externally on this object. But you can understand that it's important to produce good integrated circuit and good electronics, but to produce it is also important, maybe it's crucial to understand about the problem and also to address the final problem on a real customer. So it's very important to understand all the things that are related to the final application. So in ST exists a lot of different groups dedicated to the research, but especially exists a dedicated division that try to do the job of our customer in different fields. All the research groups in ST are dedicated to a particular, let me say, family of product or a single product. In ST, the group are divided by field and by argument. So sports, so sound, for example, security, and in this case, the field, the medical field. So just to collocate, if you remember ST in the previous slide, where was at the beginning of the chain, SRA, the dedicated division where I work, start from the integrated circuit developed by ST and try to realize the final application. In some cases, try to realize final application just to prototype level. In the other case, we try to develop the final product, certified maybe. Also in some case, in a case I will present to you, medical certified case. So just to understand the problem related to the certification, for example, in that case, and also to give to the customer the knowledge and also the to say to the customer that we are able to do this kind of thing and are we able to speak about this thing. So in this case, as I said before, exists the group where I work, dedicated to remote monitoring group, and we try to work to develop the platforms and applications in this field. And this is very important because SINTEC project explained very well our job or what we try to do, because it fit very well our job that I'm explaining to you. We develop, as I said before, different application, final application. I report here 2 real product certified medical, just to say that we try to do it, not always, but in certain cases we try to arrive at the end, hit the target. So, but not always. But in this case, we try to give a real example and also a real example of certification and try to sell, but we do not sell as ST, but also always with our partner, external partner, but doing all the things, mechanical part, electronical part, and things like this. So the message of our group, what is important for us, could be related very well, very strongly of what is SINTEC. So SINTEC, the aim of SINTEC, the target of SINTEC is try to develop something very not invasive in the measure of biomedical parameters, because in this field it's very important to do not affect the measurement. So it's very important to be not perceptible. So this is our goal, our mission in ST and also in SINTEC. And there is what we call a remote monitoring thinking for this. So it's not a problem of related only to electronical designing and something like this, but start from the mechanical part quite always, and start from the use case. So we have to develop something very easy to use, very easy to wear, because with something bulky, with something very heavy, you can ruin, you can affect, influence the final results and also the final test. If you want to sleep with something on your head, it's not easy, because if that something is very heavy, you can also not be able to sleep and also not be able to measure what you want to measure. So there are a lot of steps we follow usually, and we follow it also for to design the fix for SINTEC. So the first thing is make it wearable. So if you think in a situation, for example, you can see in this picture, my colleague, just for example, in the past, is a very old figure, I have to say, but my colleague was connected with a lot of cable in an hospital. So you can understand that it's not a comfortable situation. I have to say that it's a real situation, not probable, but real, possible, let me say. And you can imagine also the cost of this kind of exam. So our duty, our goal is to make this kind of reading, maintaining all this reading, all the reading we have in this picture, but making it wearable, like in SINTEC, for example. And again, we have to make it wearable, so we have to respect constraints about weight, about dimensions, about power consumption, and so on. But we have to guarantee a good signal extraction, and we have also to guarantee a number of different signals. Are not all necessary, the signal at the same time, but having different signal can allow to have a sensor of data fusion that can enable different parameter computation. For example, I don't know, for the pressure computation, you can think to mix up ECG and PPG to compute the pulse transit time for the blood pressure. I don't know if you already know something about this signal, but it's not important. What I want to say is that important many times to have different signal mixed up, and the possibility to mix this different signal, for example, motion with the ECG to understand the problem related to the heart and to the field. So it's important to embed a lot of different data. Obviously, we tried in SINTEC to embed all the possible data, a signal extraction in the same board, maintaining the dimension very shrinked. Not always is necessary, but it's very important to go in this direction. In SINTEC, we developed different hardwares, but I have to say the final one is what I reported here in this slide. A board very limited in the dimension. If you remember the slide Professor Klaas shown before, he showed the module, but inside the module we have this kind of hardware. So this hardware is also, you can cut in the middle, so reduce at the half the dimension, but it's not important. The important thing is that very reduced in the dimension. And on this board, we have a lot of the signal you can read on the left of the slide. So ECG, EMG, optical one, inertial motion, and also a way to communicate the bioimpedance and so on. So a lot of different signal. Our thing, if you remember the first point, make it wearable at the beginning of SINTEC, was to reduce at minimum the rigid part of our final device. So the goal, the dream is to have all the things stretchable, but it's not possible. Also, so we also thinking about the reliability of the device. In a real case, actually, we have to think a mixed solution. So we developed a mixed solution architecture where we have a different part stretchable and some part still, let me say, hard, but in this case, we reduce at the minimum the necessity, the space occupation of this. So from this signal, we can compute always the things we need. So SpO2, blood pressure, breath rate, but also other heart rate, RR variability, but also other things, more complex, maybe not more complex, but different, maybe you can think something about avatar reconstruction, something related to the motion, and this kind of thing. A disease related to the motion, so the Parkinson, so on. So following this way, we usually start from devices developed obviously by ST in our case, but not already designed for medical, quite always. So we often start from the device already designed for low power and not expensive application, let me say. So also a small part. So we started from something already designed for example, mobile application, but not for medical. But that kind of chips are very good for low power and not expensive application. So we start from that and we try to develop something medical. Example we use a spectrometer already originally designed for to correct the white in an imager, for example, in your mobile camera. From the MEMS you already use in your mobile phone to detect your motion, to analyze your motion, where we are able to collect also the data coming from potential, in this case biopotential, for example ECG and so on. So it's important to understand that our focus, our target is always to develop something very simple to use, very not power hungry, and so not expensive, and so on, guaranteeing or try to guarantee a medical grade. And at the end, not at the end, but following all the designing of this chip, these devices, the stretchability of the devices. So if you remember the first point, the wearability, what is more wearable that something is stretchable? And for this, you can imagine that for SINTEC, we follow all these points, keeping in mind that some part and the most important part of the device remain stretchable. We develop different modules, as we saw. So in the previous presentation, the important things in our architecture was that the stretchable part represents also the docking part to your body. So your feeling of these devices are already at the moment something like a second skin over your skin. The rigid part remain not fixed on your skin, on your body. From this device, as you already know, we are able to collect the data as ECG, electrocardiogram, using the board I previously mentioned. So more for the board I previously shown in the previous slide. For example, ECG, heart rate. We can compute from the ECG heart rate variability. Sorry. For example, you can also try to do other things, but just to report. We are able to measure or to, let me say, measure the electrical variation of the stretchable lines, because you can understand easily that the stretchable electronics, when you stretch the electronics, you change a little the characteristic of the stretchable lines because you are changing the area. And so if you're able to measure this variation, maybe you can measure also other things. For example, the breathing rate. If you apply the patch on your chest, you can measure the variation. The variation are related to the respiration in this case. Other things you can measure with our module are the bioimpedance. It's quite the same, but you are not measuring the variation of electrical characteristics, but you are measuring the variation of electrical characteristics of your body directly. So, and this variation is related to maybe the respiration. If you attach on the chest, maybe on the body composition, maybe on the muscle, and so on. If you see here in the image, you can see just an example when here during the apnea, you can see the heart rate behavior, and after when you start again to breathe, you can see the respiration and so on. So just a quick look of I think all the modules we've developed with Uppsala in this project, and we are continuous to develop, and with different dimensions, with target, including the battery or not, changing the connection. But we developed at the end a complex architecture, but that cover all the possible things you can try to address. And so that's it. I just want to leave with this idea that recap all the things I already said and what I said at the beginning. The importance of this technology and what we try to do every time during our job, and especially in the SINTEC project, was the first thing I said. So the technology helps when it's not reminded that is helping you. So when you have something that is helping you, is monitoring you, but you can also forget about it. So thank you for the attention.
Thank you very much, Alessandro. Let's see if we have questions, but yes, we have one. So what are the characteristics in terms of energy consumption or size of an object in this remote monitoring field?
So In general, there is not a unique answer for this, but it's important to understand the use case for the use case. Obviously, you have to guarantee for all this kind of monitoring different hours of work. In many cases, you have to guarantee days of work. This is important for remote monitoring because you are not addressing an exam you do in some minutes in the hospital, but you address a bigger thing. You can address an exam during different days, and you can also try to detect the things that happens not frequently. So very important to address this. So starting from the fact that you are working with a very small battery because you cannot give to the final user a bag with a bigger battery. You have to stay for the power consumption. We are talking about milliamps at maximum, but you have to go also below if you will monitor for days. For the dimension, it depends on where you wear this. Obviously, on your face, you have to stay in a very small dimension, and we try to address also these things with a specific board. If you go on the chest, you can enlarge a little, keeping in mind always that the dimensions are related to the weight and to the feeling of the object. So you can occupy more space, but keeping the dimension at least at the minimum you can. Okay.
Thank you, Alessandro. There is another question for you. In the applications of the vital sensors that must connect to the bare skin, how would the sticker badges deal with the hairy areas? Any solution or method to overcome this issue?
Sorry, I take in this solution or the
Yes.
child.
This issue for the to connect to the bare skin, how would the sticker badges deal with the hairy areas? So
In this
with
case,
with skin and hair.
No, there, yeah, but are always, let me say, a problem in this case, because in this case we address it to use normal patches, so standard patches, sorry, and the standard patch work well if you have not hair inside. Bottoms on the bottom part of the patches, so on your chest. So definitely you have to remove the hair where you are applying this thing. You can also to attach over the hair, but I can say from experience it's not a good thing to do. But let me say is always remain a medical exam, and when you do this kind of thing, you have to remove just a portion of the hair where you have to attach the standard patches. So we are talking about a diameter of 2 or 3 centimeters of patches. That's it.
Okay, and another question. What about the related regulations? How is the regulation process with this wearable technology?
So there are a lot of different regulations depending on the signal you are addressing. For example, in the case of ECG, exists a specific regulation for the signal, just to guarantee that the signal you are acquiring is reliable and also sufficient to address the regulation, to hit the regulation. For the other signal, photoplethysmography and so on, exist other regulation. In general, over this regulation of the signal exist security regulation and also other things related to the power transmission of data, so Bluetooth and radio you have. All this, there are 3 or 4 different regulations you have to guarantee, so to pass different tests, and you can reach the CE in this case for the European market. But if you want to go for example, in the US, you have to take another regulation. Obviously, if you take the CE here in Europe, it's more easy to have other regulation outside Europe, doing just the test, the remaining test, let me say, the test you do not perform here in Europe. But in general, exist a lot of different regulation depending on what you declare on your manual. If you declare to have a medical ECG, you have to do the test related to the medical ECG. And this is true also for the other signal.
Thank you very much, Alessandro. So if there aren't any other question, we will proceed. Okay, let's go on with
I stop sharing.
yes. Thank you, Alessandro. So, Dr. Mattei Supei is a professor of sports science, kinesiology, head of the laboratory of biomechanics, and head of the research program at the Faculty of Sport at University of Ljubljana in Slovenia. He is also a professor at the Department of Health Sciences at Mid-Sweden University for the SINTEC project. He has an interdisciplinary background with a BS in physics and an MSc in mechanical engineering and a PhD in sports sciences. He is a former elite alpine skier and a member of the national alpine ski team and demo team, and currently a member of the technical advisory board at the Slovenian Ski Association. So, Matej, the stage is yours. You can also turn your webcam on because we cannot see you. We see your presentation. Okay, thank you very much.
Can you hear me now?
Yes, very well.
Okay, hello to everyone. Thank you, Claudio, for this introduction. So I will talk about the application of SINTEC in sports. So first, why do we need to measure in sports? So that's something that is getting more and more popular, I would say, lately. It's a lot of different reasons. There are most of them health and performance related, either health or either performance or both, actually. So it is, in this case, connected to SINTEC, is to monitor and improve physiological and biomechanical parameters. And the reasons, as I said, are multiple. So it can be to monitor body functioning, fitness level. It can be directly to measure performance, to do technique analysis and detection, to look at the loads, to monitor parameters that are related to injury prevention, safety measures, equipment. So it's a lot of different options. What do you do on this? What you see on this slide is a typical measurement where you have a lot of different equipment, combined biomechanics and physiology, looking at all the possible parameters what you can measure in the laboratory. And this is not uncommon that we do such measurements at our faculty at the institute to able to help athletes. So there are two distinctive areas. One we can say it's indoor and the other thing is outdoor measurements. We do both. And also the SINTEC, what we are developing is something that could be used in both scenarios. So on the left is actually something which we've been doing for validation for the SINTEC project, which was running in place actually. And on the right is what you typically see if you do something in alpine skiing, you do some tests. It's a long area in the winter conditions, so it's totally different environment. On snow, here is sunny, but it can be also cloudy and snowy, sometimes rainy. So it's two different areas of measurements where we are interested in sports to collect data or to monitor athletes. Yeah, so wearables. So here is something that we did a while ago on the slopes. So what you saw on the first slide was what you can do in the lab. Here is a very similar situation doing on the slope with all the variables. But when we talk about variables, what Alessandro was presenting and Professor Hjort before also is we want to have something that's comfortable, that is insensitive, that is lightweight and small, not even to mention flexible or stretchable. But this is the reality, which is not very distant, and it's still used like that in sports. So for sure, we are very much interested in the technology that could be much more friendly for the athletes and much more insensitive. And yeah, that's the idea. And of course, if we look at the wearables on the market, there are many wearables on the market that are much smaller, that are much more comfortable. But we need to be also realistic. A lot of these wearables are also not very accurate, or let's say valid and reliable. So we need to be careful on choosing the equipment. So Professor Hjort already showed that the market size is increasing, and the market shares are also rearranging a little bit, but having a lot of different type of sensors in these wearables is quite popular, multiple sensors in the same technology. And looking at that, we can say that most of the signals that are, let's say, most common in the wearables is also what is included in the SINTEC project. So the SINTEC technology has been presented before, so here is just more to emphasize that size and weight really matters. So we talk about the sensors that are, let's say, 6 centimeters in the longest dimension, and the weight is in a few grams, let's say below 10 grams, as you can see on the top, which is one of the prototypes of the SINTEC sensors. We can talk something, let's say 7 to 10 grams, and compare it to a smartwatch, really lightweight one, which is below 30 grams, or a more bulky one, which is about 75 grams. We can see that these kind of sensors are far lighter and probably also more comfortable. So if we go to the application in the laboratory use, this is something from the test where we have been doing validation studies of our technology at the Faculty of Sports in Ljubljana. One is on the big treadmill and one is on the cycloergometer. So here this particular pictures, you see the SINTEC sensor only as a patch here below the chest area, and the rest is other state-of-the-art and gold standard equipment that we use to compare our sensors. And the same is on the left, so where you don't even see the sensor because it's under the suit, and the rest, the cables and the computers and all the rest that you see on that is basically just to able to have a gold standard and state-of-the-art equipment that we were able to compare how well our sensors are. And this picture now is showing step rates, frequencies for different intensities of running. And we see, of course, that we also expected here, because this is relatively simple data collection from the IMUs, from the accelerometers in particular, that this data is really well aligned with what we have received from other gold standard technologies. So here the differences were really small, and looking at standard blunt Altman plots, we see practically no bias in our sensors, and quite low limits of agreement as well, so which is in order of the state-of-the-art equipment, and we were very happy about that, and also published those results in a sensors journal. As already mentioned before, so this kind of IMUs packed in a small patch can be used not only just to look at the step rates, but it can be used in much more interesting ways. For example, looking at the asymmetries in movement. So for example, step asymmetries in walking or in running. It can be also looking in other situations where asymmetries are interested, particularly if we go a step further and use multiple sensors on the body. and create the avatar like a 3D body movement, which is also possible with this kind of technology that is under development. Alessandro already showed the ECG signals before, so we have been also interested for sport application. How well can we extract this kind of ECG signals, and when you have good adhesion between the sensor and the skin, we have quite nice ECG signals, and then of course heart rate is a minor problem with quite simple data analysis like peak detection algorithms and extracting these kind of values. And comparing the signals that we have received in our tests with other sensors, Schiller as a gold standard, or Polar heart belt as a state-of-the-art, or Garmin for Run watch, we received very comparable results with some spikes, as you can see, but this is let's say part of development where these kind of spikes can be also filtered out to have a nicer looking signals with the same quality. Breathing rate is another thing, as Alessandro mentioned earlier, which in some small portion could be a replacement for much more difficult measurement, having a mask on the face and looking at the oxygen uptake. In some cases, in some sports scenarios, breathing rate could be interesting, but so far as we learned in very extensive body movements and dynamic movements, then the signal can be a little bit spoiled by other body movements and can overlap with the signal that is taken from the breathing rate signals. So this is something that where we need to explore this a little bit further, how important it is, but for sure in more stationary sports scenarios where this can be also interested in some sports, for example in archery or even in chess playing or these kind of things, or shooting, breathing rate can be for sure an interesting parameter to measure as well. Skin temperature is also something that can be collected by SINTEC sensors. And again, here there are some difficulties, but not only with SINTEC. So the temperature readings can be, let's say, claimed as to be good, but the problem is that if you cover the skin with a patch, then you interfere with the temperature, with the temperature regulation, because you can take away the convection or even the conduction in a way a little bit, and this can interfere with what you see on the skin, because if you have a skin exposed to the air circulation, you can expect that you can have, of course, different skin temperature. And another step is then to look at the body core temperature. But in this kind of scenarios, when we were examining state-of-the-art, we saw that also the state-of-the-art is not so good at these kind of things, and we didn't want to go a step further because we know that it is a problematic area to do the measurements. The SINTEC sensors, or the smart patches with integrated sensors or active patches with ECG electrodes, for example, are connected either with Bluetooth, and another alternative is to use the SINTEC hub, which communicates with all the sensors. These sensors are then also synchronized, and this hub by itself is also a sensor. It incorporates an IMU and also a simple GNSS, and transmits the data to the cloud. And this enables very interesting features such as remote monitoring of the athletes. It enables also long-term monitoring, and what is often interesting and shown that is interesting in sport is real-time monitoring. So we can have a real-time feedback, even though that the athlete can't see the results. The coach, for example, can have an overview of how the athletes are performing and what are their vital signals. So this is another feature that is very promising for sport in combination with this SINTEC technology. So what we haven't, or I haven't been what I haven't tried yet is the technology that is being also developed under the SINTEC by Uppsala is using the fat IBC. So it's a communication in the fat tissue. So this can replace the Bluetooth communication or the cabling. And it's another interesting area that can improve, let's say, the sports measurements by reducing some other things that the athletes needs to wear, and on one side and on the other side even to improve the communication between the sensors. For example, when you have one Bluetooth sensor on the front side and one on the back side, this can have some sorts of limitation in the data transfer. So now finally coming to the outdoor use. So this is where we are the most excited, because in the lab a lot of things can be used, but going in real environment, which is typically in sports, doing all sorts of different and crazy also body movements. This is definitely the area where we see the most of the application, because it can be worn under the racing suit. It is really insensitive. It can provide you both physiological and biomechanical parameters. It's comfortable, and not to mention, it is also safe. So I mean, because of the small size, which is practically a few grams, and when you have an accident in sports, which is not uncommon, these kind of things also matter. So having any bulky sensors also during trainings in case of accidents can be problematic, and this is where we see another advantage of transforming basically the laboratory that we saw inside with a lot of cabling and bulky wearables to what is being developed in the SINTEC project. So for the take-home message, I would like you, from your own side, to think about the strengths and weaknesses and opportunities and the threats of this kind of technologies that is used in sports. So I will not make a summary of that, but thinking of what I have been talking about, I would like to encourage you also to look at the SWOT analysis that we want to do and fill out the questionnaire. So thank you for your attention.
Thank you very much, Dr. Matej. I have a question for you in this case, while we wait for questions from the chat. So are all sports, in your opinion, suitable with the SINTEC Smart Patch, or are there sports in which this kind of sensor may be not so useful? So I'm thinking to sports like swim-related activities, and also contact sports like maybe boxing or basketball.
Yeah, swimming was the first thing when you started your question that came on my mind. Everything in the water can be problematic, but I would say that with appropriate patching, instead of using a sports tape, probably we could use a tape or another type of molding of the sensors, which was one of the stages of our development, is also this, that it could be used also in water. So that's one of the solutions that I think is feasible, also within what I have been witnessing during the stages of development. So contact sports, I would say, are possible, but maybe it's more difficult in some of the martial arts, because if you hit directly to the sensor, it's probably not so good. But some of the places in the body maybe are not so much exposed for the direct hits, and there also the sensor technology can be used. Or for example, in the helmets when they use it, or in the boxing gloves in the places not on the side that you hit, or something like that. So there are possibilities also in this kind of sports that I feel that yeah, it makes it possible.
Thank you very much.
Claes here. We at Uppsala, we have recently within SINTEC tested new microelectrode arrays for ECG recording when swimming. So we have results, although I cannot say with what quality compared to golden standards. And we will lift that internally with SINTEC soon.
Thank you very much, Professor Yot. So if there are not any other questions, so we will proceed. So right now we are going to explore the application of SINTEC in healthcare and SINTEC network platform with Juan Carlos Naranjo, who is Senior Technical Project Manager at MySphera, and Jaap Koets from Evelan, who is currently working as Innovation Manager at Evelan. And Evelan, as you may already know, is a company which develops Internet of Things solutions for various fields, from industry to agriculture, from the food industry to healthcare. So Juan Carlos and Jaap, the stage is yours. Juan Carlos, are you with us?
Yeah, I'm here, but Jaap will start the presentation.
Okay. So the stage is yours, Jaap.
Thank you very much. So today I'll be talking about the application of SINTEC in healthcare. We already heard a bit about SINTEC and sports, but SINTEC spans both healthcare and sports. And I'll explain the network platform that has been built for SINTEC. And actually this platform consists of two distinct parts. One is a gateway which locally collects the data and then sends it to the cloud. And another part is this cloud solution. So I will focus on the gateway part, and Juan Carlos will then focus on the cloud part. This talk will start with a bit of explanation about healthcare and IoT. I'll discuss the architecture that we're using. I'll discuss this gateway that we have developed, which is called BaseGo, and I'll end with some conclusions. So up till now, we've mainly seen the sports use case, where we've seen that these flexible sensor patches can really provide added value to the analysis of sports performance. But these same patches and these same tools can also add a lot of value in healthcare, and that's what I will be talking about now. And why should you be interested? Why should we want this? So on the left here, you see the number of people working in healthcare at the moment. So there's about 22,000 people in Europe working in healthcare, and 22 million people, sorry. And that's out of 200 million working people in Europe in total. That means that already 1 in 9 people is working in healthcare at the moment. So that's a large number. On the right, you see the amount of money countries spend on healthcare. So this is a list of some Western European countries, and you see that as a portion of the gross domestic product, these countries spend somewhere between 8 and 12% on healthcare. So about 10% of their budget is spent on healthcare. Now you might think, wow, 10% of the people, 10% of the money, that's okay. I like my parents, I like my grandparents. I'm willing to spend 10% of my income on these nice people. However, then we come to the following graph, which shows the big problem. And what we see here is the age distribution of the European population. So on the vertical axis, you see the age. At the bottom, there's children, and at the top, there's old people. And you see here on the left in blue, the male population, and on the right in yellow, the female population. And what you see in the filled in bars, so there's filled and unfilled bars, and in the filled bars, I'll indicate it here, you see this big bulge of people in the working age. And those are all people working right now and earning money and working in healthcare. And these people are taking care of these old people here, this small number of old people at an old age. And right now we are spending about 10% of the people and 10% of the money on the care of these people. And that means that every person who's working right now has to take care of about 0.3 elderly people. But in the prediction is that for the year 2100, this situation will drastically change. So this bulge of working people will get old. There's not so many young people to replace them. So instead of having to take care of 0.3 people, we suddenly have to take care of almost 0.6 people per person. So that's almost twice as much. And where before we were spending 10% on healthcare, that then suddenly becomes 20%, and 1 in 5 people will be working in healthcare. And if we organize healthcare the same way as we do today, that's completely unsustainable. So we need a solution. And one thing which can contribute to such a solution is the Internet of Things. And here's a list of typical applications in which the Internet of Things helps the healthcare industry to become more efficient and provide better care. And they're ordered from when it's actually too late, when people are already sick, to before anything has happened. So the first thing on this list is post-hospital care. So this considers people who have been in the hospital. The treatment has been finished, but the physician still wants to monitor them to see if they're okay. And right now, often this happens in the hospital. So these people take a hospital bed. This costs around 800 euros per day. And here IoT can really contribute if you make it possible to monitor these people at home. There's an extra hospital bed for other people, and these people like it more to stay at home. So it's a knife which cuts on both sides. Then the next point is treatment. This was already discussed slightly before. Right now, it's already very common for people with diabetes to monitor as part of their treatment, to continuously monitor their glucose levels. And slowly, there's many more illnesses where IoT becomes a standard part of the treatment of their disease or illness. One step earlier in the process is diagnosis. Here we see that IoT becomes more and more common with, for instance, people with cardiac problems. They get a small sensor which they can wear, and by analyzing their ECG patterns over a longer period of time, a physician can create a diagnosis of a certain illness. Even earlier in the process is early recognition. We have some IoT projects where we monitor the behavioral patterns of elderly people, and if this behavioral pattern changes, this might be an indication that something is going on in their health. And by recognizing this early, even before people really need healthcare, we can start intervening. Preventive healthcare is even one step earlier. We have a project where we do research into sedentary lifestyles, so people who sit a lot during the day. And as they say, sitting is the new smoking. So if you're sitting, have been sitting for the entire day, please stand up, walk around the room, and give your body some release from this stress of sitting all day. But by measuring this with IoT and giving people incentives to indeed not sit all day, we prevent people from actually getting sick. And the final thing in this list is actually a combination of these various things, which enable elderly people to live at home for a longer time. And people like this because they don't want to move into a care facility. And at the same time, it makes economic sense to let people live longer at home. So these are various ways in which IoT really helps in solving the healthcare issues of the world and Europe. But within the SINTEC project, we cannot do all of this at the same time. So we focused on two different use cases. One of them is lower extremity trauma rehabilitation. So these are people rehabilitating from some injury and using various kinds of sensors developed in the SINTEC project. We monitor how they recover from this injury. And the second use case that we focus on is cardiovascular diseases. And here, as I already mentioned before, and during the talk of ST microelectronics, we already also saw a bit of this. By analyzing these ECG measurements, we can help with analyzing the performance of their cardiac system. So how do we do this? So we have several sensors, and depicted here are the sensors from ST microelectronics. And what we want is an end user or a physician to get this data and do something useful with it. This data comes from the cloud, and within the SINTEC project, we use the FiWare cloud. Only, unfortunately, these sensors do not have the capability to directly connect to this cloud and send the data there directly. So they don't have the battery power, they don't have the communication strength to do this. So to solve this problem, we have introduced a gateway called BaseGo. And what this gateway does, it on the one hand receives all the sensor data from the sensors via Bluetooth. And Bluetooth is a very low energy consuming protocol. So these small sensors are perfectly able to transmit data wirelessly via Bluetooth to this gateway. And then the gateway forwards this data via the mobile network to this FiWare cloud. Some information about BaseGo. So it's a battery-powered device. It connects data from sensors and other devices. It transmits the data via the mobile network, and then the data is available through a dashboard, so you can see it online, but it can also be made available through an API or forwarded via webhooks. And at the moment, BaseGo is used for various purposes, in research, in sports, in home care, and also to prevent heat strain in strenuous professions. And I'll go a bit further into that. So in some professions, like in the military or with firemen, there's a serious risk of heat strain. And this means that people get so overheated during training or during work that they actually suffer permanent trauma. And this means that often they're not able to work anymore, or they really sit at home sick from that moment onward. So this is a really serious injury, which we should try to prevent. And using this BaseGo sensor system, we have developed a method to monitor the core temperature of these people and thereby prevent heat injury. So this is just one of the examples that this BaseGo device is being used for at the moment. So we know now what it does. How do you use it? It's worn either on your arm or on your wrist or on the belt or on a lanyard. It doesn't really matter. It's wireless, so as long as it's nearby, it works fine as a gateway. And it has a battery, so you can recharge it via USB-C. And there's only 2 relevant buttons. So it's a really simple device. You just turn it on and it starts to work. And there's an additional button which can be used to define sessions in case you want this. So it's a wearable gateway, as I mentioned. But on top of that, it also has some onboard sensors. So it also is able to perform some measurements on the device itself. And the sensors on the device are threefold. So there's an accelerometer, there's a gyroscope, and there's a GPS. So the accelerometer makes it possible to detect the motions of the wearer, and and depending on the location where the device is being worn, it can be used to analyze either the gait or the motion or other properties, other types of motion of the wearer. The gyroscope is used in the same fashion. You use it to analyze the motion of the people wearing it. And finally, the GPS is used to locate the position of the device. And this also allows you to link certain measurements to certain locations, and thereby also link certain measurements to certain events. And this can be very helpful in analysis of certain medical data, but also in sports, it's really nice to see where during an exercise some measurements were performed. Yeah, so this is the system architecture as I've already shown before. There's actually one additional, and here it shows these STM sensors, but actually it's possible to connect a whole plethora of other sensors to BaseGo. So any Bluetooth enabled sensors can be connected to BaseGo, so you can collect data from an oxygen saturation sensor, breathing rate sensor, a scale, it does not matter. The device collects this data from all these different sensors and then forwards it to the cloud. On top of this architecture, there's one additional piece which I have not mentioned yet, and that's a management portal. And if you only have 1 or 2 devices, then you don't really need this management portal. It's not super important. But when you start to have bigger projects and you start to scale up, then this management portal becomes essential. So it allows you to perform device management. So that means commissioning of new devices, configuring devices remotely, but also end-of-life management of old devices. And it allows you to do over-the-air updates. So even people who get a device right now, we can add features at a later stage and push those updates over the air. And it also allows us to make sure that the device always has the latest security patches installed, so that communication is always secure. So to conclude, BaseGo is a wearable gateway with onboard sensors. It works out of the box. It works anywhere. It just connects to the mobile network. There's no configuration required for the end user. You just turn it on and it starts working. And some strong points are that it collects data from these various sensors, but they're all collected into a single platform in a single format. And this data is then made available in any way you would like to have it. So that's the end of my presentation. And then I've been talking mostly about BaseGo, and Juan Carlos will then discuss the next part of the data pipeline, which consists of the FiWare cloud. Thank you very much.
Thank you, Jaap. Thank you, Jaap. Great. I'm going to present you. Let me share my screen. Okay, this one. Good. I think you see my screen now. So, good afternoon to everybody, and thank you for inviting me to this presentation. And I'm going to go a little bit deeper in what we call the IoT network platform. Jan has briefly present you the system architecture, okay, where there are the sensors on the left, and there is the base code, that is the gateway, the hub that receive all the data from all the sensors from a given person, of course, and then is sent to this cloud that is based in firewall, as Jaap has said. Well, when we started designing the platform, we have several objectives in mind in order to fulfill for this platform. Of course, it should support a large number of sensors connected to different gateways, basic gateways for capturing signals in both domains, in sport and healthcare. Okay, even in the project, we don't foresee a large number of sensors and people sending at the same time the signals and all the data that is captured from the movement or from the parametric of the healthcare signals. It is possible to the platform should at least manage a large number of these sensors and gateway. Of course, the platform should process all the data coming from these sensors and provide a permanent storage for the signals for further analysis. As Jeff has mentioned, this was a requirement from the project that should be the platform, the network should be based on the IoT platform fireware. That is not because we wanted just to use this specific platform. It's because fireware is the reference, and I will explain later, is the reference architecture that European Commission has pushed in order to lead Europe, to lead this cloud, let's say, war between the different platforms in the cloud that is possible, Azure from Microsoft, Amazon, or all the different actors. Of course, because we have this sport and healthcare domain, the platform should be interoperable with different tools and different systems that these domains use for the daily basis. Should provide tools, of course, for controlling all the capture session and by the professional, even for the patients, because the platform should be operated not only by professional but also by the patients at home, for example, in outdoor scenarios. So they should be able to start, stop all the capture and all the things. Of course, as I mentioned before, should be extensible and scalable, and okay, should be a secure platform. So these are the more or less all the objectives, all the requirements that we have when we started the development of the platform. And okay, we started with one platform that is on the market, that has been developed and has proved that it's a good IoT platform. This platform is fireware, okay, that is a reference, an open architecture, but also an implementation for an IoT platform. You see in the picture there is a very complex architecture with a lot of building blocks that in the terminology of fireware are called enablers. There are some that are mandatory. There are some that are, let's say, for general purpose. You could see in the light blue, for example, the context blocker, all the data, all the big data modules, okay, service orchestration, management, authority, security, ATLs. Okay, it's very complex. It's a very complex architecture, and of course, it is extensible because you can develop on top of this architecture a lot of specific enablers that are specific for each domain. For example, healthcare or smart cities or whatever. Okay, so this is the foundation for our platform. In a more simpler way, okay, in the simpler architecture, at the end, we have these 5 building blocks. The core context management, the context broker, that is the core of the system, okay? Any, let's say, powered by fireware platform should contact, is mandatory to have this context broker. That is basically the block that manages all the updates, all the queries, all the context information about the domain. Is the core of the system. But we also have, on top of it, we have all the analysis, visualization, and so on. On the bottom, we have the interface with all the IoT devices, robotics, streaming, whatever should be connected to the platform. We have deployment tools that in this case is not very important, and this right side, that is all the layer related to the data sharing, the APIs, and all the things. Even it is include here how we can monitorize the data that is inside of the platform. This is basically fireware. And this is the very similar schema of the SINTEC platform. We have on the top, as you see here, the gateway with different sensors that send data to the MQTT broker. I will explain each block in detail later. Gateway enabler, that is a specific enabler that has been developed for the project to work with the fireware platform. We have the Orion broker, that is the core of the system, the permanent database, the storage, MongoDB. And we have on the top the dashboard, the end user environment. We have all the things related with security, authentication, identification, authorization, all these kind of issues. So this is the architecture of the SINTEC IoT platform. And if we make the map between the blocks of the fireware and the SINTEC, you see that the context broker is present. We have used one specific context broker that is called Orion. We have this interface with IoT. We have to develop a specific enabler that is the gateway enabler to make the communication, or to receive, to parse all the things, all the data coming from the sensors. And we have a visualization tool that is called the dashboard, and we have storage, and we have security, and so on. So basically, we have been inspired by the fireware platform, and we have used the core component of the fireware platform, that is the context broker, the Orion one. This is the same picture, but in different modules. You see how the data that is produced on the left from the sensors are send the data to the SINTEC gateway that enters in the platform. Let's say the cloud platform start here with when the MQTT broker receives all the data from the different SINTEC gateway that could be in parallel, will be sending the data to the platform. The gateway enabler receives the data that is connected to the Fire server. I will explain the role of the Fire server here in the middle between the gateway enabler and the Orion broker, that is the pure fireware component of the platform. All the security and the data that is flowing to the dashboard to representation of the data. Good. Starting from the MQTT broker, MQTT is a protocol, is a OASIS standard messaging protocol for the Internet of Things. What is good, or what is widely used in most of the IoT platform, is because it's extremely lightweight, publish and subscribe messaging transport. Develop software using this MQTT broker is very simple. There are small code footprint and minimal network bandwidth. That is very interesting in case of the base Go when sending the data to the platform. Basically, this MQTT broker is following, in architecture, we call it the subscriber publisher pattern, that basically decouples the client with the server. Okay, so it breaks a little bit the previous client server paradigm, and decouples different publisher and different subscribers. In this case, we have multiple publishers here. We can have potential many subscribers. In fact, we only have one in this case, that is the gateway enabler. This is basically the MQTT broker. The gateway enabler is the component that we have developed in order to parse the data that is coming from the base code. So make the transformation from the protocol that the base code send us to something more structured, more with all the, we add data that is related to the session. Okay, we make all the transformation needed to store this data into the database. So basically, it's the interface between the physical SINTEC gateway and the context broker. I mentioned before the Fire API. Well, Fire API, we use it because it's one of the requirements were we were very worried about it, is the SINTEC interoperability with other systems. Okay, in the healthcare domain, there is a standard, okay, for data exchange, that is the Fire. Fire is this standard that is published and is maintained by the HL7 organization. That is basically the more important organization in standardization of the data, of the medical data. Is using the more health records and so on. So you see here in the picture that is a very complex, let's say, environment with different layers or levels, and you see in red the ones that we have used it. We have used data models from diagnostics, for example, the observations. We have used clinical data models, for example, the procedures, that is the basically how we can model the capture session, and we also have here this exchange block that basically provides the REST API for connecting the data that we have to other systems. Okay, other systems can query us using this exchange, this REST API, in order to retrieve information and make queries to the SINTEC platform. So this is basically what we have done and why we wanted to use this Fire server in the SINTEC platform. There is a layer that all the data that is coming from the sensor is then transformed to the Fire data model and is stored in the Fireware platform in documents representing these data models. And the last part that I want to explain is the dashboard. Basically is the tool that we have for representing and for managing all the let's say the session capture, how many devices we can create, new devices, we can create new sensors and register them in the platform. We can prepare the data capture session. We can start, stop the data capture. We can do anything that the professional needs in order to retrieve the data from the sensor. And of course, we can represent this data using charts, or we can, if the professional decide in that way, we can get the data back from the database and export it in a CBS file format that is very common use in importing and exporting data for other systems. So we have this functionality. So basically, this platform was intended to be useful for the patients, useful for the professionals because I haven't mentioned, but this dashboard can be used in a mobile phone, so you can start and stop all the data sessions in your own phone when you are outside. You are at home because the doctor has prescribed you with some capture that you need to get for example, the ECG for a period of time or whatever. You can use your mobile phone to start and stop the capture of the data. And that's basically all the information that I can give you with this platform. And okay, I'm open to your question. That's all from my side. Thank you.
Thank you very much to Juan Carlos and Jaap. So let's see if we have some questions for you, Juan Carlos and Jaap, but it seems not. So we may be able to proceed with our open discussion. Let's wait just 20 more seconds to see if anyone wants to ask something. Okay, so we can go on with the open discussion and then the closing of today's workshop. So I invite everyone who wants to speak to take the stage and take word in order to, I don't know if we have once again Hank with us from Evelyn, and if he wants to share some thoughts. Hello, Hank. Sorry, Hank, we cannot hear you. You have to unmute yourself.
You can hear me now, I think.
Yes.
Yeah. Okay. Yeah. Well, thank you very much. Sorry for the confusion at the start. You would have expected after 2.5 years of Corona time, somebody would have been very professional now with using these platforms, but I guess that was not the case. So I want to thank everybody that participated, and indeed Evelyn organized this. Jaap just described, explained quite a bit of the reason why we're interested in this technology and in these applications. Our company focuses on connecting things to the internet. In this case, it is sensors. And of course, the magic starts with the technology of the sensors itself, and the statement small sensors, big data, I think is fantastic. So, and then once you have this data, you can do fantastic things with it. And we have experienced that in our own business and a lot, that once people collect data and begin seeing this real-time information, they start to get addicted to it and become more and more interested in collecting more information and add new use cases, etc. We believe this is just the beginning of some very exciting times ahead. And I think that what was shown today is clearly a nice representation of it. So if you do have questions, or if you like to discuss any of this further in a separate platform, a separate conversation, we're very happy to do that. Maybe a little bit about our own company, if you're interested in this. We are an SME in Amsterdam. We were founded about 18 years ago, based on the strong belief that IoT would become a revolution in the world. We believe it's a slow revolution, and because of the complexities that it has, but it is a revolution for sure. And we're with about 50 people here, mostly engineers, and we're focusing on creating end-to-end solutions, but specifically on the link between the asset or the sensor and the internet, because that is often the weakest link in the chain. Okay, any questions or things people would like to add to that? No? Okay, so maybe then I think we have reached the end of this workshop. Is that true, Claudio?
Yes, we do not have any more questions right now. So if you want, we can end today's workshop. Anyway, we will move to do something about the presentations that were shared today. So we will try to make them available to everyone on the project website. The project website is www.sintechscoreproject.eu. So you will probably find the presentations there once we collect them and we upload them. So just take your time to visit the website in a couple of days. And so I want to thank everyone for the participation. So Hank, Jaap, Matei, Alessandro, Professor Classiot, and did I forget someone? No, I don't think I forgot some. That's all. So thanks also to our wonderful attendees that also shared and asked some questions. So once again, I remember to the attendees that we will receive a questionnaire about the workshop and about the sensors we have been showing you today. So it would be very helpful for us and for the success of the project if you share your thoughts with us. And with no further delay, I will now close this workshop. Thank you, everyone, once again.
Thank you.
Thank you, everyone. Bye.
Thank you and bye.
Goodbye.
Thank you very much.